which is the interesting talk. So thank you, Anurag.
Thank you so much, Aranya. So it's my pleasure to be here. I was telling Aranya before that it's almost like 18 years since I've been here at NCSU. It's a long time. Before I start, how many of you have experienced power blackout? All right, well, a lot. So when you lose power at home, it's typically inconvenience for us, right? There are people in hospital, on digital life support, and they will survive battery for a few hours. For them, it's not inconvenience, it's life-threatening. You probably have seen this video from London Heathrow Airport outage, which happened this year in March, which impacted, not only London Airport, but several other airports, and a lot of people could not travel, right? We all know that power outage also impacts several different infrastructure. So, this projector is working with the power. This light in this room, all the digital technology, internet, everything needs power. So other than inconvenience to us, it's basically life-threatening for someone. It's a billion-dollar budget per second if you count at the world level outage, and does impacts all the infrastructure, right? So infrastructure, what you can think about, from water to gas, from transportation to nuclear energy is essential. Right? Without that, these are not going to work. Now, the second thing is how does we operate this power grid? I mean, if you look at any critical infrastructure, we do have a control room to operate the infrastructure. Either it's a transportation, or it's a water or gas. So in this case, in the power grid, the control room looks like this. How many of you have been to control room? All right, quite a few. So now imagine that you are operating a biggest man-made machine ever on planet Earth. You are one of these desks. 2021, you get a lot of alarms. In Texas, that temperature is falling. Then you get an alarm that gas pipeline has been frozen. Then you get an alarm that generator is out, line is out, and you need to make a decision to stop that. You need to make a decision to not impact people, thousands of people. And then you start getting alarm that power outage happened here, and then here, and you're not trained that how do I handle this situation, because we never had this kind of freeze in Texas in the past, right? You need to make a decision, and Texas freeze was not the only thing that happened. We see storms, we see cyber attack, we see wildfire happening more and more, and then of course hurricanes, right? Which sometime will come to North Carolina too. So with all these events, the question becomes, how do we train? How do we give tools to these operators to make a better decision without causing cognitive overload and without causing, impact on the grid or minimize the impact on the grid, right? So a different thing that will happen with these events is that your infrastructure will also get damaged, which means that we need to know in the power grid operations center that resources is gone, load is also gone, building is gone, and keep updating, right? Because assets are impacting too. So the real question is that what we can do about it, right? I mean, of course, there is a lot to do. We cannot talk about it in 1 hour. I mean, I can spend several years to talk about what can be done. Few things I'll discuss today is that first understand the problem better. It's not an infrastructure problem. It's also a problem of physics, respecting physics, also a problem of math, and also a problem of understanding the cyber, if you look at the cyber attack, understanding the weather, if you look at the weather impact. And then, once we know the problem better, then what tools I can develop to make job of these operators better, so that they can make a right decision and minimize the impact. And then the third is, because I cannot validate these tools in the real grid, right? It'll be too late if I validate and say that, oh, it failed. I need a test bed, which is as real as a power grid, real environment, and scalable, and will tell me that these tools are going to work or not, right? So at least I need these three, and this is what I'm going to focus today, right? So the talk today is about cyber, physical, human, and an effort to link these three. By end of this talk, you will see the connection between cyber, physical, which is power grid here, and human resilience. So I will be focusing mainly on cyber, because in the theme of this, we have to pick one event which is impacting the grid more and more. And next few, I think 1 hour or less than 1 hour, I'll be spending time in these four things: that understanding the challenge, what tools are needed and how we can develop that, again, understanding the math and physics behind it, and then how we can use that tool to validate and enable resilient grid, and then finally summarizing it. So let's start with the first one, which is understanding it better. So the power grid, just like any other infrastructure, you have an asset. Again, that's the biggest man-made machine ever, infrastructure, where there are loads, which is building, offices, industry, and then they get power from distribution lines, and also from DERs, which is basically co-located with these buildings. Then we have a transformer or substation, which you'll see if you're driving in any urban environment. You'll see a substation, which is that's where the transformer is located, which is converting the power from high voltage to low voltage, so you can distribute it to your loads. And then before that, there is a high voltage line, which is getting the power from larger, generating stations, which will be hydro, coal, nuclear, and a bigger power plant. So all the assets, of course, there are many things here for control, is being sensed locally first, which means that each substation has a data collection box, digital devices, analog devices, which will sense that which state you're operating. It will process those and then send few things, not all, few things to a control room server. And from there, we will get to the control room, which we just saw that how it looks like with multiple different desks. The key things here important is situational awareness and decision support, which means that situational awareness means that knowing that what state we are operating. Everything is normal. If not, that what I can do to make it normal. We can operate in normal. We can operate in, failure mode, some failure mode, which is, we classify that as a alert, which means some failure, but it's not impacting everything. And the second will be emergency, which means that more things has failed and causing the problem. And then the fourth state is restoration, which means that how do I restore and comes back. So we typically keep moving between these four states, and alert and normal happens every day, right? While emergency happens sometime, and restoration is following that. So once we get to the alert or emergency or restore, decision support becomes important. Before that, everything is operating as expected. So situational awareness is more important than decision support. Another way, when things fail, then when decision support becomes more important. So if you look at the power grid in layer-wise, then you have asset power layer, which I just talked about, generation, transmission, distribution, consumption. Control layer, which is basically that's where you put your sensor and actuator, bunch of digital and mechanical and electrical devices. Communication layer, where you use that data and send somewhere, right? And then you have to put a security layer on top of these. So at least IT security, a little bit of OT security already in place. And then application. So you have objective, which is the first objective is to, in fact, if you look at the objective, it has been always same in almost like 150 years, that we want to make the grid more reliable, which means that ability to supply all the connected load. Resilient, which means that even if I am failing in alert mode or in emergency mode, I'm still able to provide some critical loads. Economic, we always want to operate the grid in such a way that it's the most economical, and customer should pay less, right? If the bill should be less, because everything that is happening in the grid, who is paying for that? Is customers. Secure, which is operational security, which means that even if one, and that's a requirement from NERC, which is our federal authority, and FERC, that even if one asset fails, system should be operating as reliable as possible, which means that all the loads should still be met and supplied. And then stable, and a lot of different stability here. So we steady state stability, transient stability, dynamic stability, and that basically refers to keeping the key parameter in the power grid to stable scenario, either it's voltage or frequency, which we understand a lot because voltage should be around 120 at 110 that we get at home, and then frequency is 60 hertz. If anytime we drift away from that, life of our appliances at home, our industry will deteriorate, right? So if your fridge, refrigerator, or any machine that you connect to this grid, which is not at 60 hertz and 110, it will not perform in the same way as it should. And then sustainable, which means that we should have enough energy resources now and for the future to keep operating our planet Earth. So applications are basically around that how do I make it economic, which is either market or without market, different application to keep the stable security, resiliency, and reliability requirement, and energy management system is a software tool which we use at Power Grid Control Center, and then utility control management system for billing it, and then several different engineering services. So now let's get into the more cyber aspect of this. You have probably learned about the periodic table. This is about ICS, OT, cybersecurity. There's a lot of terms, right? So we cannot talk about all. Few things which relates here, and one thing that you always deal with every day is IT, which is also part of the power grid, and then how do I support the cyber infrastructure? But then there are some other things like ICS, which is the industrial control system, which is not common, which is slightly different than IT, because this one is control system, but for physical implication. If one fails, asset will fail, people will lose power. PLC, which is a programming logic controller, which used to be kind of like a default device at most of the substation to get the data in and send it and then give the control action there. Slowly being replaced with more advanced IEDs, which is intelligent electronic devices. Then there are some protocol like DNP3, and so a lot of these different things. Another one which is very common at substation is RTU, which is a remote terminal unit, which typically substation will have, again, get the data in and then send it to the different control room. So I'll not go to all of these, but basically, other thing which is important is the Operations Center, which is SOC, Security Operations Center, which is also known as NOC or Network Operations Center or NOC. What is important that things are changing. Vulnerability in the power grid comes from the cyber. Anytime you connect and send data, vulnerability comes, and if you connect more and more devices to that to provide services, vulnerability will increase. IoT devices, which is DERs and batteries and all those things can think about. This year, it's expected to be 41 plus billion IoT devices, right? Other thing is vulnerability also start with the same human employee which has access to IT and also has access to OT. Because if they get compromised, if their computer get compromised, and they have access to OT devices, any attacker can use their computer to get into the OT. This is how it happened in Ukraine cyber attack in 2015 and 2016, that employee computer was compromised because of phishing attack. So, I'm sure that all of you get a lot of emails. And even if 1 out of 1,000 or 10,000 click on one email, that is enough for attacker to get in, right? So think about that open house with the door and windows. Unless there is a door and windows open, attacker cannot get in. So if you follow all the security protocol, attacker will not be able to get in without significant effort. So they need an open door or open window, and that comes through one way of phishing attack where employee will click on a link which will install a malware into your computer, and that malware will allow attacker to monitor and then find the password and other authentication to reach to the substation devices, which is part of the OT or operational technology. We are sending more and more emails, more and more social media, more way to get connected, which is increasing the vulnerabilities because, of course, phishing does not need to come only through email. It can come through LinkedIn. It can come through Facebook or Instagram or any other social media you can think about. 5+ billion email. And then if you think about how often we exchange email, 376 billion every day. Then you look at the CVE, which is very specific to the control devices tied with infrastructure. So we collect, this is called cyber vulnerability exposure. These are the known CVE which exist and might have been patched by the vendor or might have not been patched. So these CVE, how do we learn about that? One researcher or government-funded organization are always doing pen testing or penetration testing for these IEDs and devices, which is operating the grid, operating other infrastructure. And then by pen testing, they will find the vulnerability that this software has vulnerabilities or any part of the device has the vulnerabilities. They will publish it that here's the vulnerabilities. Before publishing, they will inform the vendor, wait for a few months so that they can fix it, and then tell the world that this still exists. If you're not fixing it, you are vulnerable. This is the open door and open window in your substation for attacker to get in. Some get patched, some do not, right? And again, these vulnerabilities only one way to get in, right? Some vulnerability are very well known, like default password on one of the digital devices, which remains same and no one has changed that, right? And if it's a default password, then of course it's another vulnerability which will not be published here. But remember that these vulnerabilities is coming because we are knowing about that through pen testing. There are other which we don't know, and those known, if exploited, is called zero-day vulnerability, which we don't even know how many exist, right? even though we have thousands of people in US just looking at vulnerability and doing pen testing, but it's just effort to find out who will find first, attacker or defender. So now, given this background, the next thing becomes, well, if something is compromised, something is not normal, how do I know that? And then we look at the next part, which is anomaly detection, that you need to know first what is the problem before I can fix it. So how do I detect? We need to look at the data, what data we are getting, right? So you're getting data from physical system, you're getting data from cyber, which are different kind, different types also, and some could be structured, some could be unstructured, some could be time series, some could be streaming in real time, and some could be residing somewhere as a log file, and you need to, or non-streaming data, you need to dial in and get in those data. Some are static data, some are dynamic. Some has concept drift, which means that what is normal now with this data, after 1 hour it will be abnormal because we don't expect that, which means that the definition of what is normal and not abnormal is also changing for some kind of data. So it's not a simple problem as it seems that, okay, let's get data, apply some machine learning, and you got it. And even if you detect something, you don't know that what kind of anomaly it is. Is it expected or it's unexpected, right? Is it happening because every day, every second, we are having anomaly in the power grid because, someone is hitting the pole, driving the car and hitting the pole. Someone is in a normal scenario, tree is falling online, or one of the device, a sensor, got heated and stopped operating in a way that it should. It's not a cyber attack, but it's an anomaly. So even if I detect something, how do I differentiate it? Is this a sensor failure? Is it a data problem in cyber, which is a cyber anomaly? Or it is a physical event which is causing this problem? So as soon as I detect, we need to classify it. And if I classify it as an event versus a bad data versus a sensor problem, event, which is a physical event or cyber event, I need to also localize it so we can rank it that how critical it is, how it's going to impact us. And then find the root cause, because root cause, if I can find it, then I can fix it better. Just like if you go to a doctor, if they can find it, you have a symptom, why that symptom is there, they cannot fix in a best possible way. So here, same thing, if I don't find the root cause, I'll still take some action immediately, right? And then I'll find the root cause and take care of that as soon as possible in a best possible way so I can fix the problem thoroughly. And everything, these need to be done in a second, right? Which is, otherwise, grid is connected and every disturbance will propagate at a really fast rate. So now let's look at the second thing, which is what tools I can develop, which will help with this thing, like anomaly detection, classification, ranking them so I can prioritize and make a decision, right?
Can I ask a quick question?
Yes.
So in the first part, can you quickly explain, like, specifically what kind of attacks you're referring to? Like the popular ones are denial of service, where communication links stop sending messages from one end to another.
Mm-hmm.
The other can be fault data injection, which is like a corruption kind of an attack. Then there are other, like GPS spoofing is there, there's replay attacks. So does it matter what kind of attacks the grid is facing, or is it applicable for all categories?
It will be applicable for all if we have considered that hypothesis in our tools, which means that we have already analyzed that if this happens, this is the characteristic of the data coming from the cyber and physical. So we have worked on basically through Grid X, which is a NERC exercise for the power grid, which P&L host and we worked directly with them. So P&L was part of the team. We worked on MITRE framework, which is basically any kind of these attack, you can map on that. But even though we have analyzed more than 30, 40 different kind of attack vectors, but we had to focus few, which we analyzed all the way till the operator testing. So yeah, I'll talk about that, those things. So getting the tools, so start with the same thing that we want to do real-time detection and monitoring, which is detection, classification, and then once it is an event, not a bad data, then classify it and localize it. So first thing is event detection, and you can use the data from PMU, you can use the data from SCADA. SCADA will be, of course, slower, and then you have to use the data from cyber, right? So we treated these two different because these two data are very different type, different characteristic. We cannot apply the same principle in a same way to cyber and physical data, right? And it has to be multi-step because some are streaming and some are non-streaming. Some are structured, some are not structured. So first, physical data, PMU data, you can apply to differentiate between event detection and event and bad data, and simply we just apply Prony analysis because it can differentiate between something which is happening because of bad data versus something which is happening because of physical. And then you can choose a very complex machine learning method or very simple because you want to do that quick, very fast. Plus, it's a concept drift, which means that even if you use very complex machine learning, how do you train it? Because the normal versus abnormal is changing over time. So we started with very simple linear regression, Chebyshev, and DBScan, which is different kinds. So one is regression, one is, Chebyshev is more like a statistical, and DBScan is more like a clustering, right? And then to classify it, we basically worked on a different type of event and what is the signature of that in active power, reactive power, in fault, in unknown event, and how I can differentiate with certain pattern because each has this certain pattern. So we applied Shannon entropy and forming subgraph. Then we did the graph sweep so we can, again, localize it in a smaller area for the location of the event. Now, this is not the only way that we came up first, right? So we have written more than 30 papers on this just anomaly detection, classification, localization, which means that we have tried 10 different theoretical approaches and 15 variations of that to come up with that, right? Yes? Yeah, so that's a very good question. That if you detected the bad data and event perfectly, then everything is fine. But what if you detected that bad or wrongly? Then you took out the event and put in a bad data, which will miss it, right? So we are kind of doing that first together, and then we are still flagging it, which means that we are not taking that out. We are still only flagging it. So later, during the classification stage, if that bad data, which was designated as an event, or event which was designated as a bad data, need to change, it can. We still have opportunity to change that because the pattern looked in the classification stage and later is showing something else. So it's a little bit more complex because if you get the bad data out, your process signal will look different, especially in time series. So you want to flag it and still keep it, and then reprocess it again and again till you get confirmation 3 times, yes, it is a bad data.
So basically reducing the possibility of false negative.
Exactly, yeah. So very simple technique applied here. You take the PME data. The first thing we found that one technique is not going to work, right? Because it has specific characteristic and there's no single winner. every technique, doesn't matter that you use a complex or simple, need parameter tuning, right? And then training data is not available because abnormal event does not happen very often. So we finally finalized like ensemble-based approach, which is unsupervised, because we can take care of concept drift, we can take care of this. But we did apply, like I said, that a lot of these technique, which I cannot list all, but we have tried random forest, we have tried Euler transform, we have tried LSTM, we have tried autoencoder, we have tried autoencoder transformer, we have tried GCNN, which is a graph convolutional neural network, we have tried physics informed variation of machine learning, and then we're still doing it because we are not getting the 100% result. We still get 95, 98%, right? So we are not targeting 100% because that's all not possible, but can we get 99% or 98% at least? So we are still continuing this work, and it is different for dynamic event versus steady state event and versus, like considering concept drift. So you can find a lot of these papers that you've written over the last 10 years, decade, if you're interested in any of these. So continuing that, like most recent, we looked at dynamic event. If you have a dynamic, transient or dynamic event, which is also happening because of, sensor problem, which has a similar signature at the generator level, then it was difficult to detect through some clustering or statistics approach because it's happening for a short time. So we developed a technique. The only problem is that it has to work at a substation. It cannot be centralized because every generator signature is different, or most of the generator has different signature. So we developed this, which we call decentralized modular nonlinear PIN, or physics-informed neural network, which is only working with the set of equation from that generator, because we know the generator and we know the control. So we can model those set of equation and can do the algebraic and differential equation, and then put that into the neural network as a two different cells, as algebraic and differential integrated cell. So this was giving pretty good result for each, even though we tried like applying it the same one for two different controls and two different generator, but it did not work. So, and did not give us as higher accuracy as it will give for one generator. So now we talked about a little bit about physical data set, and you can apply the similar principle to SCADA, which works perfectly with the unsupervised because it's not a fast rate of data. So second thing become a cyber data. And the cyber data anomaly detection tool, which we call CDADT, what we did is that, again, you're getting this cyber data, which we can classify into structured, unstructured, following standard protocol. Some are time series, some are, again, streaming, non-streaming, dynamically changing. So here, what we did is that we applied first sticks, and cyber data, of course, does not need to follow physics principle, right? Because it's not coming from physical system. It's coming from cyber. What it does need to follow is if there is a specific standard protocol, it does need to follow that, rules and regulations. So we can apply that kind of simple rules, right? And once you do that, then the second will become applying it to a simple format, which we use sticks, which is from Idaho National Lab, to have the data in such a format that you can apply different machine learning approaches, right? We'll apply rule-based first, because we know that this has to follow certain standard protocol. And then, after rule-based, we'll apply some machine learning. So in this one, which we are, again, something that we are continue to work on, we have applied different technique. This one is very simple autoencoder, and which works actually not bad with this set of data, and we are continuing to apply more and more method. Now let's get to the comprehensive look. So you got the SCADA applied with simple statistic or machine learning based algorithm, which is respecting the physics. You got PMU data. Again, it has to come from this, respecting the protocol, which is GNP3, Modbus, and SCADA, C37.18 protocol for PMU data. And then the cyber data, which is applied with the network traffic and OT, and host log, sys log, which we can get that too. So finally, we will get some detection here and then intrusion detection there. You have to combine this and you have to rank that. So this is anomaly, cyber anomaly or physical anomaly, and this is more important because it will impact the system in a larger way. So we apply this resiliency metric to rank those. What is resiliency metric? Is basically saying that ability of system to keep supplying power when these events are happening, or these anomalies are happening. So we can use that and rank these after detection and classification before even look at the root cause. So I take care of that and take the control action as soon as possible, then find the root cause and take more comprehensive set of action. So we have this physical event, then cyber event. So these are the tools that we developed. Of course, EMS already exists. We worked with a company called PingThings, which is came out of UC Berkeley. Sync ADC is something that we have developed. We have developed the resiliency metric, CP-TRAM. Splunk is again a standard software in any network operations center or security operations center. CDADT is the same tool that I just talked about for anomaly detection in cyber data. And then we have a cyber physical event, which is all these things together to take care of that, right? So over the time, we have worked on multiple different resiliency metric tool and also decision support tools. So in 2018, we developed this Canvas, which was for cyber attack and network vulnerability analytics software for distribution system. 2019, we developed Cypher, which was mainly for military macrogrid. And these are being used, actually. Then in 2020, we developed this more comprehensive CP-SAM, which is not only give the metric, but also give you the ways to rank them and take a decision or help with the decision. And then 2023, we developed this transmission-focused metric tool. And then most recent, which came out of another DOE project recently, last year, we completed with MIT and Princeton on CP-RIM, which is a distribution system with IoT devices. So as you can think about that, each of these tools was done with collaborator, right? So for example, in CP-RIM, which I'll talk about, we had Princeton doing something, which is part of our tool. We had MIT doing something, which is part of our tool. So this part, you have distribution system and you have a lot of these IoT devices connected together. First thing we need to make sure is that you trust that IoT devices if you want to take the services out of that. So how do you trust? That's a federated learning process, and that part was done by Princeton. What we did is that how do I develop this trustability score? Using their metric or using their output and using other data that we can provide. Once we get this IoT trustability score, using that, we'll find out PNR, which is primary node resiliency score, which is a one level up, which is basically right here at this node, this transformer. And then from here, you can go all the way till the substation, which will be the next score of distribution system resiliency. So most of our resiliency metric works factor-based, which means that if I define resiliency as my ability to keep supplying critical load even under failures or contingency or anomalies, what will stop me? And if I can list those factors that what will stop me in doing that, I will calculate that factor, combine that all together, and then give you a metric, right? So this is how we did, and that's what you see, that different factors listed here. ITS trustability score, we can compute, and then apply some, your math and some different approach which is established that how to combine the factor. So for example, you can use multi-criteria decision-making process, which is AHP in our case, analytical hierarchical process, AHP, which will take these factors and combine that together. And then finally, you get this distribution system resiliency metric. That was the goal for this. Again, the privacy preserving part was also done by Princeton. So we just adopted what they have developed.
So where is the human model in this?
Yes, coming. Oh. So all these tools will be used by human to make a decision, and that's where we get the human part. So this is one of the tool, using all these metric, different kind of metric, and then it can help as it gets alert that what's going on with the system, and CVE-based impacted buses. By the way, this is Washington State system because that's where I used to work, and I continued that system because I had access and even at West Virginia. So finally, it will give me a resiliency metric, all the different factors, and then same thing, I can look at the cyber, and as I get the alert, cyber alert, and which CV is getting compromised, I can use that based on that decision that, okay, this CV is compromised, so I have to make this another decision compared to another CV, right? We have to map that, and then remember that you will get to the point that you cannot map to the CV because we don't know that. So that's a zero-day vulnerability. We still can take action on that, and I'll show you how. So let's get to the defense. So defense has to take something that already exists, right? So we have a network segmentation, we have a anomaly management in some way. We just strengthen that part with respecting the physics of the grid and domain-specific knowledge for DNP3, IEC protocol, whatever you have, right? Then monitoring incident response, which already kind of exists. Again, we strengthen that. Access control, we also worked on that with SDN, and network segmentation also we worked on software-defined networking. Patch management, which if you develop CVE, then of course you need to patch it. Very important thing is training and continuous improvement. So let's take this network segmentation part as an example, even though we have worked on all of these in some way. So this is network segmentation part. So SDN is basically designed for, more flexible networking aspect, right? It was not designed for security, but we took that and used that as an angle by finding analogy that typically in power system protection, you use relay. And relay has multiple settings, like 6 different settings that you can switch between. Can we do the same thing with the software-defined networking, which is predefined? And as soon as we detect something that has been compromised, you change to option, basically setting 2, and from then setting 3, and then setting 4. So we use that, and of course you have a much better control with SDN networking, that who will talk to who, right? Remember that if access, and if you want to have this door and windows closed, but you still want to open because you need services, then you only open to neighbor house, not to, anyone can come in. So same thing here, I will open to specific devices. And then we compare that, okay, if things fail, which performs better, right? So it's very clear that resiliency metric is very high for full SDN, and full traditional, it's very low, right? For 2 different scenarios. Of course, it will cost me money, because if you implement SDN, then it will cost you more. But we did also looked at hybrid, so you find a balance between cost and enhancement in resiliency. So this is how we tested and validated, and we delivered this to SEL so they can launch a new product. So now looking at more DER and IoT devices, let me talk a little bit about electric vehicle as a restoration service, which was another DOE project that we worked on. Typically, we are operating in multiple different modes that I talked about: normal, alert, emergency, and restoration. And if you say that emergency and restoration is resilient mode, and alert and normal is economic mode, because that's how we do. Then you can subclassify them as economic versus resilient mode. The objective is different. In resilient mode, you want to use all the resources available to you, which includes electric vehicle. So we took example because this was also a project with MIT. So we took example of Boston and electric vehicle where we put, and then we took the road network. You can take the electric network and change both into a graph, right? And then we can look at different scenarios. So electric vehicle is providing services at where they are, at a charging station. But if there's electric bus, you can actually move it with a bunch of them from one location to another location, not too far, if you want to provide a power in an island. And if there is a big storm or hurricane, it will also damage the road network to move it, right? So now you got transportation island, you got electrical island, and we are using EV as a services to provide that. So objective becomes that how do I provide the services to grid resources, which is grid load, using, of course, conventional system, which is a grid power supply, and electric vehicle, and battery, and DERs. And then I can formulate that, write all the equation, write all the constraints, right? And then you get to this problem that there's electrical island, transportation island, and I want to do that as steps because I don't need to move EV if it's not needed, right? So first thing will be that let's restore the power using all the static DER, not moving EVs in the system. And then in the second, I will use those community-owned vehicle, which is like electric bus, electric truck, which is large enough and is owned by city, owned by county. So I have more control over that, right? And then the last will be using those EVs, which is owned by consumer. We can only use it if they have signed agreement in advance, right? Which is like a demand response. If they have not signed it, we cannot use it. So with all these three steps, most probably you will be able to solve everything here. You don't need to get to the moving electric buses, but if needed in an island, you can. And then the third one, which will be moving another thing. So finally, this optimization problem, which gives me the solution of EV optimal location, routing, and allocation, destination, and DER to restore the power in this emergency scenario, we can also solve the same optimization problem in distributed way. Why? Because if something has happened and impacted the transportation, of course it has also impacted your cyber, which means that you cannot send the data from those, and we know firsthand because I also helped a lot during the Hurricane Katrina in Mississippi, and Georgia Power and others, Mississippi Power, to basically develop the strategy to survive. So cyber also, data will also be gone. That's expected. And if that happens, the distributed optimization is more resilient because it will work with where the nodes are left with, right? And still provide a solution compared to centralized. So now let's come to the last part, training validation. That's where we bring all the aspect, including human and cyber physical. So now you got these tools. Now we have to put that in front of operator. And let's see that can operator use it. And then we are looking at now different metrics. So we looked at metric, which is, tells me that what is the resiliency of the system, which tells me that is it anomaly or it's an event or whatever it is. Now we want to put in front of humans, so we have to still look at those metric, but now we have to look at that I do not do cognitive overload of operator. I respect cognitive flexibility. And we understand the cognitive memory, which means that how much I can remember, right? Which is, I think, at least 5 years before, it was a very new area for me, and I learned a lot from my collaborators. So let me talk a little bit about that. So we have these two testbeds. One is electromechanical, one is electromagnetic, and then one control room-like environment, which is a mini scale. The good thing is that most of the EMS that is in control room does not consider dynamics of the system. Why? Because vendors are not they are thinking about it, and maybe in future they will, but right now it's a steady state system operation, right? But in this lab, we can actually bring the dynamics to here, because we do have a test bed which can model all the way polytronics dynamics, all the way substation, which is right here, and then RTDS, so Typhoon, so everything dynamics we can model. And we integrated that dynamics with the EMS, which is from Inksys Power Simulator, which is from company from Seattle. And then we have all these tools, which is CPTRAM, CPSAM, Sync AED that I just talked about. And then modeling tool for network, which is NS3, SDN, Splunk, which is typically used for network open center, SNART, and PingThing, which is a really good database tool. So now I got everything together to measure those metrics, but also human metric. I'm doing two things. One is stress monitor. So we put that something on their finger to see that how stressed they are while making decision. Second one is this eye camera. So I can see that what they're looking at the screen and track their eyes. You can also track their pupil size, because if they're stressed, then it will enlarge. And if they're not stressed, it will become normal, right? So I'm sure that when you talk to someone, you can figure out this person is stressed or not, because this is what your mind is analyzing. You probably don't realize that, right? So we got all these things, and then we got a set of questionnaire prepared by cognitive science expert. So I can see that, and I can measure the cognitive flexibility versus cognitive overload, right? So we did that. We worked with our local utility system from West Virginia to Ohio to Pennsylvania to Washington, D.C. We gave them money. We invited them to come to our lab. And power grid operator works in Sept, right? So they don't work every day, which means the day they are off, they can make some money by coming to our lab. So we had almost 30 operators coming to our lab. We put same EMS that they are used to seeing in their control room. But the EMS is up, the data is coming from the simulated or emulated power system, right? Cyber is real because there's a real network, there's a real cyber attack, there is a real devices. And power grid is simulated because we cannot, generator and transmission line, of those are simulated. And so the DERs and IBRs. And then we asked them, okay, we will give you a tool and will not give you a tool where you can make a better decision. We will observe your cognitive science behavior, we will cognitive behavior, and then we will provide our tool, which is Sync AEDC and other things, and CP-TRAM, and then say that now, okay, can you make a decision again and see that, what decisions you will be taking now. So we looked at, 4 different attack vector, which is actually each attack vector is a series of attacks. And this is driven by Grid X exercise, which is the biggest exercise that we do in the power grid, NERC Grid X. And again, the same guys helped us to do that from PNL. I also work at PNL, by the way, as a scientist. So, and then we looked at the MITRE framework to map these things, right? So initial access discovery. And we actually really followed these things because cyber and digital devices are real. So you can do a real attack launch. Of course, we need to isolate our lab from the university network and make it a little bit protected so that any malware, everything will not reach where it can cause a harm. So as you see here, with all these tools like human, eyeglass sensor and then stress sensor, all the data collection that we do, and then we use this iMotion software to analyze everything. And then finally, we had a transmission operator, distribution grid operator. We also used some power student who knows about power and some non-power student to make a decision. This one is very clear that transmission operator made the decision first, right? Not surprising result, but very obvious result that they will be the first because they're used to that environment to make a right decision at the right time. While a non-power student, even though we gave training to each of them, will take more time to do that. Other interesting result was, looking at their performance in terms of cognitive overload. So if the cognitive overload, which means that you are giving them a lot of information, right? If you give them a lot of information, their performance will basically slows down and pretty quick. So that's why we say that, our mind is not a multi-thread machine, right? Our brain does one thing at a time. And if you overload it, the performance will not be good. So same thing here. If we show them that, okay, look here, and look here, and then open this PDF file and make a decision, the performance is going to be really, really bad. So we have to provide them minimal information. If they are power grid operator, don't tell them that it's a cyber attack. Just tell them that the decision is that this is probably you have to call network operations center guys because this is not your expertise. Just leave it to them. This is what we need to tell them through the tool. They don't need to think about that this is cyber, this is a power attack, this is what needs to be done, right? They will get the alert and they will get the decision, suggestion, right? They can think on that and then they make a decision. Other thing, you can see the cognitive ability, which is a cognitive performance, which is flexibility. So cognitive flexibility versus performance is almost linear. What is cognitive flexibility is something, your ability to do things that you're not trained for. So you never got trained, can you make a decision for that? Now this was very, very interesting. In normal scenario, if someone has higher cognitive flexibility, they will think too much. And they will delay their decision-making process, even for normal things. While in emergency scenario, you want higher cognitive flexibility, in normal scenario, you want someone who follows rules, who does not think beyond. So less cognitive flexibility, right? So what do? In normal, we want an operator who has less cognitive flexibility. In emergency, we want a person who has higher cognitive flexibility, right? So there are a lot of different solutions that we, suggested in our report and paper. If I can track that somehow, like every 3 months, I will do a testing and then figure out that this operator has a higher cognitive flexibility, this one has less, I'll make a different lead, different supervisor to approve those processes, right? During normal and during emergency. That will be one way to do that. And remember that everything that they do, supervisor has to approve it. Really, and they are on the floor in the same room. So all these things is important as we allow them to make a decision.
Does the decision need to be taken by just one individual, or can it be team-based?
Typically, it's done by one individual, but they do have ability to call, talk, and even call the neighboring control center. And even the decision that they will take, it will go through supervisor. Plus, they always have a support team to talk to. So if they are not sure about something, they will just text the support team that do the analysis, do the engineering analysis and tell me.
So shouldn't these curves be based on like some kind of average cognitive ability of all the people who are making the decision? Not just one person is doing that, right? So he's taking inputs from everyone else.
Yes, but the decision need to be made by only them, right? So they can take support from others, but other people are not making decision, right? So here also they had the same role to play. They had access to cognitive engineering team. Well, they had access to the engineering support team. They had access to supervisor. They could have called, right? So just to summarize, I think the most interesting result was that how different cognitive abilities are more important in normal and operating, in emergency scenario. And then one thing is sure that power grid is going to and already having more and more digital devices, more and more assets which can provide services, which also brings vulnerability, attack surface, and risk, right? And how do we handle that? That will be really important. We do have a lot of these assets which is not designed for these services because at least like DERs are only providing a specific services, not a resilient service. If they do, it will provide an added value for DER adoption or renewable adoption. One thing is sure that we need to provide tools so that operators are not overloaded. We are making our system complex to operate, but mind has not evolving, right? I mean, brain is same. That, in fact, it's a controversial thing that with all the reliance on AI, we are making our brain better or worse, right? So if they're not learning, they're not going through struggling, they're not advancing their brain, right? We are not doing anything other than training them, doing through the drill. So they definitely need advanced tools because we don't want cognitive overload and bad performance. ML need to be used, but we need to be very careful that we do respect physics, domain, and all those things, and we do apply that. So at least in the power grid, I'm very big on physics-aware or domain-aware ML. So it takes a feasible action. Detection is, of course, can help us in corrective, but also in proactive action. And if you take proactive as much as possible, while still not increasing the cost too high, that should be the way to go, right? And then finally, the human aspect, and then how do we interplay this cyber versus physical versus human, right? Because if you can detect, at least for cybersecurity issues or cyber intrusion, if you can detect that in the cyber before it hits the physical, it's much better, right? And before the physical hits the human layer, if we can handle that in physical system, we are avoiding, and unfortunately, human are the weakest link so far in all the attack vector that we've seen in the world. So we have to protect them, and we should not even think about taking human in the loop out and put the autonomous control, because it will bring more vulnerabilities and more impact, right? So you're not thinking about even the human is the weakest link, we still want them, because autonomous control is more vulnerable and much more impactful on the grid, right? So all these three layers, how to interplay, there is no ideal perfect solution. It will be always trade-off and multiple ways to do, but all this analysis is something and discussion is needed more and more. With that, thank you once more. And if someone asks you that, can we make the grid resilient? Answer, hopefully, after this talk, if you have not been exposed to resilience, that answer should be yes, we should. And we should have started that on yesterday. That's the need of the day.
Any questions from the audience? Or lots of questions?
Sure, yeah.
Yeah, thank you, Anurag. This is a great talk. And I've developed software and testbed, so I know how much effort would go into a comprehensive research like this. Mm-hmm. So I have two questions. One is about the cognitive ability. The other one is about resilience metric. So, how did you measure the cognitive ability of the operators?
Yes, so the two things that we're looking is cognitive overload and cognitive flexibility, right? So there are actually, of course, it was done by my collaborator, but there is a famous test which is done through the card, right, to assess the cognitive flexibility. And then there are a set of questions you can ask, which will be, another way to learn about cognitive flexibility. Then the iMotion software provide us this heat map that where they are looking at, which will provide us about, if you analyze that, it can be converted into cognitive flexibility because they are looking at the right, part of the screen where they should, even without training. So it means that they have a higher cognitive flexibility, right? So all these three things, we converted that to a score. For cognitive overload, you can see at the pupil size, and then you can look at that how distracted they were while looking at different part of the screen. So these were the two used. Again, it was done by collaborators, but this is what my understanding is, yeah.
Thank you. Second question is about the resilience metric.
Yes.
So this is a subject that I don't quite understand. So your expert opinion. So there are many metrics defined in the literature, right? Different papers look at different things. So how do you determine which ones could be more useful for English?
Yeah, so like I said that, all the solutions that we look at, none of them is perfect. Every metrics will have a trade-off. Like if you want a comprehensive or not, and we do have this IEEE, well, there are 5 different IEEE PS and SIGRE working group. And after participating in all of those, my conclusion was that we don't need a one metric, but we need a suite of metrics. And how do we select at one time? The metric should tell me that it will perform better if you're looking at after the event, before the event, right? Or during the event, if there's a metric, because we can't do much during the event, but if it exists, it should tell me that when it will be a better, right? So any metric which is also telling me that what factors is considering and where is the application will be ideal thing to do. Yeah.
Good. Thank you.
Thanks.
Yeah. So a couple slides back, you had a picture of the HIL, I believe it was the HIL resiliency testbed photograph. It seems to me that this would be a really great area to explore digital twins.
Yep.
Right. So building it physically, you could essentially simulate it with a digital twin.
Yeah, totally agree. Yes. So for digital twin, of course, we need a feed from real system or from another parallel testbed, which we can call real system. So we have done actually some work in that and also published, which we call, one of the paper that we wrote last year was digital twin to help with the cybersecurity decisions. Yeah, thank you.
Any other questions from anyone? Maybe I can ask this to answer the question. So, when you spoke about the physics-informed neural network,
yes.
So you said that there's one NN per generator, right? Like you are installing like a
at substation, yeah.
At any substation, and then you train the neural network with all these different equations, the physical equations. So what is the uncertainty or what is the unknown there? Like if everything is already known, then you don't need an NN. Right? So NN is something when you are making some prediction because of something that you don't know about the system.
Yeah, so here you're predicting using neural network for the next measurement, and you're comparing that with the real measurement. So we can tell that this is an anomaly or not because measurement is not matching with as predicted, right? And that's why you need a very highly accurate neural network for each generator which can do 99% accurate prediction.
But if you use a general model, can't you just predict the measurement using models?
It will be challenging because you cannot get any training from the last data. So it's a deterministic model with a set of equation. At the same time, while neural network, it can learn from the data in the past too. Right?
So you assume that there is some uncertainty in the overall system model.
Yes, the behavior, yeah.
All right, let's thank the speaker one more time.
Thank you.
Thank you for showing so many things. A lot of.
Oh yeah. I think
It's amazing how many software families you guys have developed. Like this.
Hey, can I?
Sure, yeah.
I have some questions. I'm currently working on some research that might be I want to be muted.
Yes.
Confidential.
Let me just disconnect here.
Anyway, I'm working on some research with where I'm supposed to be incorporating physics-informed neural networks.
Yeah.
So I'm doing symbolic regression, modeling electrical engineering systems, or CERDES or something like that, anything. So the idea is that once we get past the proof of concept with symbolic regression, the idea is that we will incorporate physics priors.
Yeah.
So I've been doing some reading on physics-informed neural networks for that purpose. So my question for you is this: have you found any how did you find the sweet spot? You're like, do I encode a lot of things? Do I encode too few things? Because that is the problem.
Yeah, that's the problem. problem because
time-consuming thing. So my thought process is like, okay, if I want to incorporate all of the behaviors, then I want to take any expression and break it down as much as I can and incorporate